next presenter is Wole Jaiyeoba from the University of Virginia. He's a 7th-year PhD research student at the University of Virginia, advised by Professor Kevin Skadron. He is passionate about accelerating applications running large-scale workloads using FPGAs. His current research is tailored to accelerating graph analytics using high bandwidth memory on FPGAs. During this project, he has filed 2 patents with Samsung to propose efficient methods to tackle random memory accesses on the FPGA. Well,
thank you, everyone. So today I'll be presenting my work, ACTS. It's a near memory FPGA graph processing framework. My advisor is Kevin Skadron. Graph represents key workloads of modern day computing. Essentially, they allow us a framework for analyzing relationship between things. Graphs are ubiquitous, found in several application domains, and there are a variety of graph algorithms available out there today, depending on what kind of information we're trying to extract from data. Now, there are some challenges with graph processing: frequent data movements, extremely low computation to communication ratio. About 80 to 90% of processing time is spent on just moving data around, and about just 10 to 20% is spent on actual computation. Graph processing also exhibits poor spatial and temporal data locality, and they're also memory bound. So these are the challenges with graph processing. Now here I talk about a very widely known abstraction for graph processing called gather, apply, scatter. It's a widely known abstraction for parallel graph processing. And the idea is, the reason it's widely known is because it can generalize across several graph algorithms. And by simply changing some functions, 3 functions, you can move from one algorithm to another algorithm. With the gas decomposition, every vertex maintains what's called a state. And in the gather stage, a vertex accumulates information from its neighbors. The apply stage, the vertex applies this accumulated value to change its state. And the scatter stage, it scatters this updated value back to its neighbors. Now, there are a number of variants of the gather, apply, scatter abstraction. There's a push style gas. And the idea is that vertex updates are pushed from source IDs to destination IDs. There's the edge-centric gas, gather, apply, scatter abstraction. And it's the idea that we're iterating over edges rather than vertices. Now, this makes more sense using high bandwidth platforms because with several graphs, there are more edges than there are vertices. So it makes more sense to stream edges sequentially from memory and then make random accesses to vertices stored in on-chip BRAMs. So in this work, we employ the edge-centric push-style gather, apply, scatter variant. Now, FPGAs are now very competitive platforms for graph processing. They support very high off-chip memory bandwidth, as well as high internal SRAM bandwidth. So this is massive processing potential. But graph processing applications are still yet to harness all of these potentials for 2 main reasons. The first reason is throughput challenges. Because of the unstructured nature of graphs, we have runtime data dependencies. I'll explain more about this in later slides. And this prevents us from harnessing all of the SRAM bandwidth potentials in FPGAs. There's also the scalability issue with graph processing. It's where we have several parallel FPGA accelerators demonstrating excellent throughput with very small and tiny graphs, but then their performance begins to break down as we scale to larger graphs. So we address these 2 issues in this work and essentially propose an FPGA graph accelerator that can perform competitively well with larger graphs as it would with smaller graphs. So this is an overview of my presentation. I'll discuss the scalability challenge with FPGA graph accelerators and how we address this challenge. Essentially, we employ an online partitioning mechanism where we resort to partitioning vertex updates rather than the edges of the graph. I also talk about our recursive partitioning idea that allows us to lower partitioning overhead. A very interesting insight with this idea is that we're able to trade off more partitioning steps for higher HBM read-write efficiency. I also talk about an optimized edge layout with, that allows us to represent edges efficiently in HBMs, such that these edges can stream onto the FPGA and eliminate on-chip data dependencies. And finally, I'll briefly talk about an optimization we have for handling sparse frontier subgraphs. I'll give evaluations and I'll conclude. So the scalability challenge with prior FPGA accelerators. Now here we see the very conventional pipeline used by several FPGA accelerators. You have the scattergun apply running on the FPGA, and then you have offline preprocessing where partitioning is done. So because FPGA accelerators heavily rely on the use of on-chip resources to make random accesses to vertex properties, to handle arbitrary graph sizes, that's graph sizes that are much, much larger than the on-chip capacity, they resort to some form of graph slicing. And the idea is that you take a graph, you slice it to multiple parts, such that the vertex properties associated with each slice can be staged in on-chip BRAM or ultra-RAM resource. But there's a challenge with graph slicing, and this challenge becomes more evident as we scale up to larger graphs. The challenges are, number one, some vertex properties will be read more than once, and also some vertex properties will be read and never used. That's while processing each slice. So while this challenge can be very negligible with small graphs, it exacerbates as the graph problem size increases. So this is the scalability challenge with prior FPGA accelerators. Now to tackle this challenge, we propose to, rather than making partitioning an offline activity before the slices are loaded to the FPGA, we make it an online requirement. But more importantly, we partition vertex updates rather than graph. So when I say partitioning here, I mean restructuring the locality of vertex updates rather than those of the edges of the graph. Now, the very important point to note here is that doing this would allow us would ensure that vertex properties are read only once from HBM in every gather, apply, scatter iteration, irrespective of the graph size. And essentially, we can maintain a fairly consistent read bandwidth usage of vertex properties across increasing graph sizes and essentially enhance scalability. So these are the contributions of our work. I'll give more details about the first three, and then I'll just give a very simple basic slide to illustrate the fourth one because of time constraints. I've talked about our online partitioning mechanism. I'll talk about our recursive partitioning idea and our edge layout strategy, and an approach and a hybrid access to process sparse subgraphs. An important thing to note is that all of these contributions essentially improve the scale, the throughput across the entire graph processing pipeline. The first contribution is to lower partitioning overhead. I've explained why we resorted to online partitioning rather than offline partitioning. But online partitioning can itself be a high overhead task because we're dealing with arbitrary size graphs, and trying to partition a graph online can result to some form of fine-grained data movements between on-chip memory and off-chip memory. And the impact of DRAM access latency comes into play and decreases partitioning performance. So here I show a very simple partitioning workflow where you have vertex updates generated from the scatter stage and represented in HBM. And this vertex update are streamed to the FPGA in chunks and partitioned using the high speed resources of the FPGA, for example, into 4 partitions in this example. And these partitions now loaded back to the FPGA. So this process continues until all the updates have been partitioned into 4 partitions. So basically the locality of this, the BRAM locality of these vertex updates have been improved. So we propose a recursive partitioning idea. And the main goal behind the idea is to maintain a fixed number of buckets, irrespective of the size of graph we're trying to partition. In the previous bucket partitioning idea I showed in the previous slide, as we scale up to larger graphs, I think I should show that. As we scale up to larger graphs, the number of buckets we'll need, on-chip memory buckets, would have to increase. Now, the problem with this is that with large graphs, if we start having fine-grained data movements between block RAM and off-chip HBM, and this increases the DRAM access latency and degrades partitioning performance. But with our recursive partitioning idea, we split the partitioning task into multiple sweeps or steps. And the main idea behind this is to manage the DRAM access latency, to manage the granularity to which data moves between off-chip and on-chip memory during the partitioning process, and manage the DRAM access latency. In this simple example, we have vertex updates loaded on-chip to the FPGA partition into 2 buckets, fixed number of buckets, and then these partitions loaded back to the HBM, and the second sweep does the recursive process, loads each of the 2 partitions, further partitions into 2 further partitions, and at the end of this partitioning process, we still have 4 partitions. So there's a trade-off with our recursive partitioning idea, and is that we have more sweeps with partitioning, but we trade that off for lower DRAM access latency, and this has shown to be worth it for larger graphs. Second contribution of our work is to tackle on-chip data dependencies. So graphs are highly unstructured, and that's because an edge can connect arbitrary pair of vertices together. But there's a problem. Because of this unstructured nature, when processing these edges on on-chip FPGA, we can have multiple edges accessing the same vertex properties in the same block RAM memory in a given clock cycle. So this is some form of serialization. And this limits the amount of BRAM parallelism we can harness on the FPGA. So this is what I refer to as data dependency issue. So the solution we provided is, can we restructure edges or represent edges in HBM all during pre-processing, such that as these edges are loaded onto the FPGA, we can have concurrent accesses to vertex properties across both source and destination dimensions, and essentially leverage all the on-chip parallelism the FPGA has to offer. Now here I'm showing that this issue of on-chip data dependencies is present across the entire graph processing pipeline. So tackling this problem will allow us to essentially boost the throughput of the graph processing pipeline on-chip. So we present ACT-Pack, and the fundamental insight behind ACT-Pack is to group edges in sets or what we call edge blocks, such that as these edges are loaded from HBM on-chip to be processed, they can make concurrent accesses to source vertex properties stored in on-chip BRAMs or ultra RAMs. And then when circular shifted as shown in the figure, they can make concurrent accesses to destination properties also stored in ultra RAMs. So this will allow us to resolve the dependency issue, because an edge as shown in the figure can access neighboring vertex properties. But more importantly, the most important insight behind this is that no 2 edges in a given edge block can access the same ultra RAM in any given clock cycles. So we can maintain concurrent execution of edges on chip. So here I show how our ACT-Pack, how edges are rearranged using our ACT-Pack idea. You have a graph, you divide the edges of the graph into intervals by source IDs. You divide the intervals into groups by source and destination IDs. You arrange the groups into sets and you form edge blocks from these sets. The main difference between our edge packing idea and that of prior arts is that our edge packing idea allows concurrent accesses to source and to vertex properties across source and destination dimensions. Whereas with prior art, as shown, their packing approaches allow concurrent access across a single dimension, and then they have to resort to shuffling or arbitration for efficient accesses across the other dimension. The third contribution, which I'll just very briefly highlight here, is an approach to process sparse subgraphs. Now, it's widely known in the FPGA community that the edge-centric style of processing is not very efficient for processing sparse frontier subgraphs. By sparse frontier subgraphs, I mean, for example, with algorithms like breadth-first search or single-source shortest path, where you have certain iterations where not all the vertices are active in those iterations. So the approach we use to tackle the challenge here now is with processing such sparse subgraphs with the edge-centric method, you can resort to reading or streaming out edges from HBM with only few edges actually being used. So to solve this problem, we take a sparse frontier subgraph and label regions of this subgraph as either sparse or dense. And then we process these sparse regions of the subgraph by reading edges from compressed sparse rule format, and then the dense regions of the subgraph by reading edges from our ArcPack edge representation. So what we're trying to do here is to capture the distribution of sparsity that exists in a frontier subgraph and essentially minimize the amount of unused edges we're reading from HBM while processing such subgraphs. We implemented ACT on a HBM-enabled FPGA across multiple processing elements. Each processing element was connected to a separate HBM channel, and each processing element executes the gather, apply, scatter functions. And then we distributed the processing elements across the different superlogic regions of the FPGA and had inter and intra synchronization modules to allow synchronization of data after every gather, apply, scatter iteration. So this is how ACT is represented on the FPGA. We evaluated ACT against GraphLily. GraphLily is a state-of-the-art FPGA graph accelerator that also uses the HBM. And Gunrock, a widely known used GPU graph accelerators. We implemented ACT on and GraphLily on the Xilinx Alveo U280 board and Gunrock on the NVIDIA Titan X GPU. We also use the gap benchmark suite as our CPU baseline. Now I'll show results for PageRank and single source shortest path. On the y-axis, we show speed up over gap for GraphLily, Gunrock, and ACT. On the x-axis, we show the different data sets. The first 6 data sets are relatively small data sets, and the last 6 are relatively large data sets. So as we can see, the blue bar represents GraphLily's performance, while the brown bar represents ACT's performance. The very important thing to note here is, as we scale up to larger GraphLily begins to tank down in performance. So it expresses very good performance with small graphs, but then the performance begins to degrade rapidly as the graph size increases. And that's because of the limitations I had mentioned earlier. But ACT, which is the brown bar, maintains fairly consistent, competitive throughput compared to Gunrock across both small and large graph sizes. And the results for single source shortest path show similar behavior, where GraphLily experiences degraded performance as we increase graphs, the size of graphs to run, while ACT maintain fairly consistent competitive throughput compared to Gunrock. So in conclusion, the FPGAs provide impressive potential for accelerating graph processing, but there's still work to be done on the FPGA, especially in the area of scalability. Can we have FPGA accelerators that would be able to deliver impressive performance with very large graph as it would with very tiny graphs? So that scalability issue was what we intended to tackle in our work. And also we provided techniques to improve the throughput and to essentially allow us to leverage more of the on-chip BRAM parallelism available in the FPGA. Thank you. Questions for the speaker?
First question, I mean, looking at your paper, the data sets are all designed to fit in HBM. If the graph is huge and doesn't fit in HBM, do your techniques still benefit? I mean, what do you do at that point?
Yeah, so currently this work was for just a single FPGA. So we didn't evaluate scaling across multiple FPGAs, but we expect it to still behave the same way because the main idea is basically to restructure vertex updates, and if it works efficiently with one FPGA, it should scale to multiple FPGAs as well.
Great talk, thank you. I'm just wondering, so there are several graphs with different properties. For example, there are graphs that have many nodes that are well connected, meaning that have so many edges, and also other graphs that means the number of edges are relatively on a more smooth distribution on different nodes. So will that affect your edge packing technique in a sense?
Sorry, can you repeat your question again, please?
So the graph normally follows like a power law, right? So some of the nodes are very well connected. For example, a social graph, that might be a celebrity or whoever. They have many connections. There are other nodes who are not that well connected. And if that skew is higher, will that impact that edge packing technique that you proposed?
Yeah, thank you for your question. The different data sets we tested had these different properties, and we still saw very low overhead. There is space overhead from empty slots with our edge packing techniques, but we didn't have more than 5% of that overhead, even with very well connected graphs like you mentioned.
I guess you used the Titan X as a comparison for fairness, right? Because the bandwidth had to be roughly the same, the peak bandwidth. My question is, what if, okay, of course, it wouldn't be a fair comparison, but how would it compare against the latest generation NVIDIA GPU that have roughly 4 times more peak bandwidth and have been shown to achieve very high percentage of the peak bandwidth with their parallelisms and whatnot?
Sorry, I didn't get the last part of the question. Did you say how will it compare with the latest and
yeah, like
NVIDIA
A100, for example?
Okay. More bad. Okay, yeah. So yeah, we used this Titan X because it was fairly similar throughput with the FPGA, but we did run analysis on the NVIDIA Pascal P100. It has HBM, almost 2 times the bandwidth of the Alveo board. But one thing we realized was the performance advantage using this P100 did not reflect its bandwidth basically. So it wasn't 2 times the performance of this Titan X GPU. And so we just left it at that.
So then you also gain in terms of energy efficiency, I guess.
Yes, yeah.
Okay, we better stop it there and thank our speaker.
Thank you.